So I will see. So in the previous class, you can see this color, right? So, d omega square is basically d theta square plus sin square theta d phi square. Okay. So this is known as the Schwarzschild geometry. Okay. So first exact solution of Einstein's field equations of general relativity and obtained by Karl Schwarzschild. And this basically describes the metric. This is basically a vacuum solution of Einstein's field equations, spherically symmetric vacuum solution of Einstein's field equations, and it basically describes the metric outside a spherically symmetric star radius capital R. Is fine. We are not deriving it. We shall derive it later from. We shall learn how to get this solution from Einstein's field equations later. But if you have a star like this, spherically symmetric star, so this is here, the space-time geometry outside the star is described by this metric. Okay. Now, yes, what is the problem? No, that is fine. That is fine. Don't worry about that. So, when you will see, if you want to see, then you will see the problem. Okay, good. Now, I told you that in the previous lecture that suppose you have someone sitting over here and he's emitting some signal with frequency omega star, then the frequency that one receives at infinity, omega, which is omega infinity, this is the frequency of this same signal received at an infinite distance from this object. That will be given by 1 minus what we have seen earlier. It was 1 minus so the frequency that you will see at infinite distance that we derived earlier from that rocket thing by applying the principle of equivalence, we showed that the relation was this. Now, today our aim, as I mentioned earlier in the previous class, that we shall try to derive the same result using this geometry. Okay. For that, let us consider the following figure. So you have P and R and P. And suppose that, by the way, you can let us call this capital. Okay. Let's call this capital R or RS. it's better to call it capital RS. Okay, and suppose here you have some observer. Is a stationary observer situated at this radius. Okay, and another thing is that I will say that the radius of my star is equal to this. Okay. So this direction is near cap, and this direction is. And there is some stationary observer here, and light signal is being emitted, and that is being received at some. This is some arbitrary radius of small r, and small r is much greater than capital R. And this light signal is being emitted not necessarily in the radial direction, it is in any arbitrary direction with frequency omega star. So this is the radius of the star. From here, light is being emitted with frequency omega star. Not necessarily in a radial direction, but in any arbitrary direction. And here you have the stationary observer. Some observer is sitting here. And it is being received at this arbitrary radius, where there is another stationary observer. His radius is much larger than capital R. Okay, and let us see. I mentioned to you that the energy in general relativity G, A, B, and these are all stationary observers. For convenience, I will just delete. I will call this as UB. Okay, this is my notation. UB observer, the four velocity of the observer. So, in order to measure the energy of the particle, you need not only the four momentum of the particle whose energy you are measuring, but also the four velocity of the observer. Right? So, I'll assume that this UV, which I called as your observer, is now this thing, which is normalized to -1. Now, what is this thing? This thing you can write it down as GAB, UA, UB.
So we are using the description of C, so this should be minus C square.
Is equal to. You can do it. You know what it is. Okay. So GAB, you can write it like this. And this is a stationary observer. Let us assume that this is stationary. What will happen? If this is stationary, then so all these observers are stationary observers. The one who is emitting the signal and one who is receiving the signal. Both are stationary observers. So if it has only this zero component, and therefore this we can write it down as G naught naught. Because all other components are zero. When you expand this, is this point clear or should I do it? It is clear because let me just do it for once and it will be clear to you. So these are repeated indices, so it is summed over. So you just sum it 0, V, Q0, UV plus UV. I is running from 1 to 3. now you expand B. So this will be 0, 0, U 0, U 0, plus again I component, but G0I is it is diagonal matrix of by component 0, so that is gone, and UI is already 0 because there are no special components, so that term is gone, so only G00 this term survives. Right? Now this is equal to -1. This would imply this implies that U0 square is equal to -1 by 0. And what is that? G00 is this thing with the minus sign. So you will get 1 divided by 1 minus. Okay? G00 is this full thing. So minus minus cancels and you have this. So if you have this, then this therefore means that U0 is equal to okay, this is what U0 is. So what can we write down now? We can therefore write down the following thing, that U A observer is equal to okay.
What is observer? That it means sitting and arrays or
In general, this is a function of r, small r. In general, this is a good question for which observer. In general, for any stationary observer situated at any arbitrary r. This you can write it down as where what is IA? Right? Right, Nagi? So UA observer is this multiplied by sin. So this is a time-like vector. It's a vector in the time direction, along the time direction. This particular vector has a name. It is called killing vector. Killing. It's called a killing vector because it tells us that there is a particular symmetry here. What is that symmetry? That is this is a time-like vector. So if you move along the time-like direction and you note the form of the metric, you will see that the metric components G00, GRR, they do not change along the time-like direction. So along the time-like direction, the metric does not change. So there is a time-like symmetry, time translational symmetry. And this time killing vectors basically give you the symmetry vectors or tell you about the symmetry directions. Okay, so UA observer is this, and now we are ready to calculate what E is.
So, sir, depending upon the metric, the killing vector of, killing vectors will be different for different symmetries.
This particular metric is a static metric because the metric components do not have any t dependence. So if you move along the t direction, there will be no change. So moving along the t direction is a symmetry. So this is a time translational symmetry. So this vector is a time-like killing vector. Now let us calculate capital E. Capital E, by the way, you can contract this, you can write this as PA UA. I'm not writing observer anymore. You remember that there is something observer. So E is equal to this accident.
That means along the killing vector, the observer doesn't feel the effect of the metric at all.
No. The time, if you move along the time-like direction, there is no change. There is no change in the metric. But why will the observer not feel the effect of the metric? Metric though is there, but there is no change in. If you move along this direction, metric will remain the same. Okay, so E is equal to this. But what is UA? UA is this multiplied by the killing vector, time-like killing vector, where xi A is 1000. So you can write this as xi A multiplied by okay. Now if you have this expression, you can now say that at this point, when you are at R, capital R, you just remove this. R is equal to 2gm by c square. C is 1, so let us remove this also. Let us forget about this. Let us forget about this. Anyway, I think this is not a very good notation. Let me not call this R is equal to 2gm. I'll tell you what. This is not R is equal to 2gm. This is the radius of the star. Otherwise, it will be a problem. This is any arbitrary radius. This is not 2gm. Okay. This is the radius of the star. Let me just write it down here. This is the radius. Don't confuse it with RS. RS is this thing, but RS and R are unequal. So if this is true, now when you are at this point, this is the surface of the star, and the observer who is stationary here, he is emitting the signal, and that signal has frequency omega star. So what we can write is this energy E is equal to h bar omega star, and that is equal to this smaller will now get replaced by capital R. So this will be 1 divided by 1 minus. For convenience, I can write this down as RS by R. Because 2gm is RS. Since C is 1, 2gm is RS. So this is RS by R. Because this smaller is capital R. Now, at this position, at the radius of the star. So this is a square root. Keep down. Second. H omega star. I'm writing it down. I will. So now this is PA is IA evaluated at R. And you have this factor. This is when the signal is emitted with frequency omega star from the surface of the star. So energy E, that is equal to minus PA UA. That is minus PA UA is nothing but UA, you put it. UA is this factor multiplied by xi h, and evaluated at capital R at the radius of the star, and that I equate it to h bar omega star. Is this clear? I hope this is clear. And when you receive it here at smaller or at infinity, right? At infinity, because you want to take this limit ultimately to infinity, there we have h bar omega infinity. For r infinity, this is 0, so this factor is 1. So what we shall have is minus EA psi A at infinity. Clear? Should eta just be clear that this is capital R, this is not RS. Because RS actually for this kind of stars, RS is actually much less than capital R. RS is actually much less than capital R. You can actually calculate it. Because if you put in the mass G and divide by C square, you will get a value of RS for this solar mass thing, and you will find it to be about 3 kilometers. 3 kilometers, but radius of this white dwarf, suppose if this is white dwarf, this is 1000 kilometers. So it is much smaller. So just make that correction, this is not equal to 2 GM. Okay. So if this is clear, if this part is clear, now we shall make an input. The input is the following, that this P is IA is a constant along a geodesic. It's a constant along a geodesic. Now, what do I mean by a geodesic? A geodesic, roughly speaking, we shall come to it in details later. A geodesic is basically the shortest distance in a curved manifold. The shortest distance between connecting 2 points in a curved manifold. Just keep this in mind for the time being. This PSIA is a constant along a geodesic, not along anything else. We shall prove it later. Once we learn what geodesics are, we shall prove this result. But for that, we need to have the understanding of geodesics. So if that is true, then you can basically set this and this equal, or what you can say is that since this and this are equal, therefore h bar omega star is equal to 1 divided by 1 minus Rs by capital R square root h bar omega infinity. Because this and this are equal along a geodesic, but since this and this are equal, and this is equal to h bar omega infinity, therefore from this equation you have this relation. Okay, so if that is true, then
This is constant along geodesic. How can you say that?
এইগুলো সব রেডিয়াল জিওডেসিক্স এর মধ্যে পড়ছে। And you can always use that fact. You will take that particular trajectory where this is, where you can use that property. So you have this relation. So omega star is related to this by this, and therefore from that relation you can immediately see that from this relation you can immediately see that omega infinity is equal to and this is the exact relation that I told you you will get exact gravitational redshift relation. So it basically tells you that the frequency of the signal or the energy of the signal that will be measured by an observer, by a stationary observer at infinity, that will be smaller than the energy of the signal or the frequency of the signal emitted from the surface of the star. So this is smaller than this because it's a negative sign, and therefore it tells you that since the frequency is smaller, therefore it is redshifted, and the redshifted is due to gravity. So this is gravitational redshift. So this is the exact relation following from the Schwarzschild geometry. And now, you know, Rs by capital R is very small, right? Because this is 3 kilometer and this is 1000 kilometer. So you can make a binomial expansion, and therefore you will get Rs by 2r omega star, and if you put what Rs is, and you can now restore back c square for dimensional consideration, from dimensional consideration, because gm by c square is actually as the dimension of length. So length by length is dimensionless. So this is the result that I derived earlier from that equivalence principle, rocket. This was the approximate relation, and this is the exact relation which you can derive from the exact metric, Schwarzschild geometry metric. Okay. Do you have any questions at this point?
In the rocket prescription, there is some discrepancy that doesn't lead to the actual result.
Because you are using some Newtonian equations and things like that. That is why you are getting some approximate result. Because we started, that was the first problem that you pointed out.
Yeah.
All these are Newtonian.
Yeah.
We are using Newtonian equations. So no wonder that we were not getting the exact relation. We were using Newtonian mechanics. Or Newtonian gravity rather. We were using Newtonian gravity. So that was the reason that we were getting that approximate result. But it is not a wrong result. It should be consistent. So if you work out from a more fundamental theory, which is the Einstein's theory, you get the exact result, and which reproduces the approximate result in the appropriate limit. So this tells us that everything is fine. And this is all about what I wanted to tell you about the gravitational redshift. The only things that I have not mentioned to you here is that I have assumed two things. I have assumed the Schwarzschild metric that we shall do later. How do you get the Schwarzschild geometry? And the second thing that I have assumed is that this is a constant and a particular geodesy. But to prove that result, I will prove that result in a couple of lectures. This is not very difficult to prove. We shall prove it. But to get to the Schwarzschild geometry, it will take us some time. Okay. So if you have any questions at this point, you can ask. Otherwise, we shall proceed.
That means time-like symmetry will also generate the energy conservation also.
Yes, yes.
If there is a space-like killing vector, then we will not able to do this kind of work. No, energy will not conserve.
Is some sort of energy conservation. And this factor that you are getting here is basically called the gravitational redshift factor or the gravitational time dilation factor. Now, from now on, we have to look at the mathematical part, and we shall start doing some geometry to go deeper into what general relativity is. So, let us consider a curve. Let us consider any arbitrary curve. Gamma. So, this curve I call it gamma. In some manifold, there are some objects that I shall, some terms that I shall take. This is a manifold. Manifold, roughly, you can, I will not give you the rigorous definition of manifold is, but you can think that any curved surface is a, you can think of it, you can call it a manifold. Example, the surface of a sphere, that is a manifold. Okay? And on that arbitrary curved surface, you have some curve like this, which I call gamma. Okay? And it is described, the curve is parametrized by lambda. Is parametrized by lambda, and in any arbitrary coordinate system, it is described by the coordinates xa lambda. In any arbitrary coordinate system, the points on this curve is described by the coordinates xa lambda. Lambda is the parameter with which the curve is parametrized. And you can define functions of these coordinates defined on this curve like this. These are functions of these coordinates. What we wish to calculate is the following. We wish to calculate the rate of this function is this f is a function of these coordinates. This function is a scalar quantity. It's a scalar. Okay. It's some number. There's no indices, right? So if you go from one frame to another frame, you will get the same number. It's a scalar quantity.
So then you define a function along the path, right?
You define the function. It's a function of these coordinates. The coordinates are basically the points on this curve. So in some arbitrary coordinate system, you have this point as something.
At that point, you define that function.
And the card is on some manifold.
Curve is on some manifold, on any arbitrary manifold. And what we wish to calculate is the rate of change of this function f along the curve. So we wish to calculate.
It gives some kind of velocity like.
It will give some kind of velocity, as we shall see now. We wish to calculate what? Curve is parameterized by this parameter lambda. We wish to calculate the rate of change of this function f with respect to this parameter lambda along the curve. Example, if you are confused with this description, example, we have seen already an example. You can think of a circle. Circular equation, what is the equation of the circle? X square plus y square is equal to a square. Now the same circle you can write it down as what? X is equal to a cos theta. So theta is a parameter. So circle, those are the parametric equations. The same thing like. Also, the example of the uniform acceleration problem. You have seen the functions as the x function of tau. That was c square d cos hyperbolic g tau by c. So those are written in terms of, actually you got a hyperbola, but now you are writing it in terms of parameter tau. So those hyperbolas are parameterized by tau. The same thing here, so you want to calculate this, and this you can write it down as del f.
So f can be any function.
F is any function, any function. So you can write this. This is chain rule. Okay. So from here, this procedure immediately allows us to define two different quantities. Fa and Ua. What is Ua? This dx d lambda. So this is what? This is a vector. I will define. I will tell you rigorously what a vector is. It has a particular transformation property. So Ua is this. It's a vector. And what does this vector tell you? It tells you that is basically dx d lambda. So at this point is basically a tangent vector. So this UA is a tangent vector to this curve comma every point UA. So this is a vector, or more precisely a tangent vector. And what is this? This is called a dual vector. It's a dual vector, which is basically nothing but accident. Which is basically nothing but the gradient of the function.
So that should not be x a lambda is equal to f a usually. That should be f is equal.
I'm not writing x lambda is equal to f. I'm writing here to here. This is, I'm calling this fa. Since the index is here, I'm writing it down. This I'm calling it to be. Okay, this is a dual vector. Now we would like to look at the transformation properties of these objects. Suppose I make a transformation of coordinate transformation from xa to x prime, from xa to x prime. Under this coordinate transformation, fa x, I'm writing in short x, ua, this is also a function of x. This will transform to f prime a x prime. Okay. Or it is just let us look at the individual transformation property for the time being. Let us look at only this thing. We will do this one later. So this is what this is a scalar. So you can just forget about this. So this will be just del f del x prime a. Now you just put the chain rule here. This will be del f del x b. So this object, this dual vector or the gradient of the function f(x) under this coordinate transformation goes to this thing, and this is equal to del f del x prime a. Now you apply the chain rule del f del x b del x b del x prime a. B are repeated indices, so they are summed over, and this is equal to del x b del x prime a, and this particular thing is nothing but fp. So this is 6. Okay. Let us now, under the same transformation, let us now look at what is UA. How does UA transform? UA function of x transforms to U prime a function of x prime. That is equal to d x prime a d lambda. That is equal to del x prime a del x d. Correct? Again chain rule. This is in this coordinate system dx prime a d lambda. Now you apply the chain rule. B repeated, so it is summed over, and therefore this is equal to del x prime a del x b dx b d lambda. That is nothing but. So you can see that under this coordinate transformation from xa to x prime a, this tangent vector to the curve at any point, this transforms in this way, and the dual vector, which is the gradient of the function, this transforms in this way. So anything which transforms in this way, we shall call it to be a vector. More precisely, since the index is on top, we shall call this to be a contravariant vector. And anything, any object which transforms this dual vector, which transforms in this way, the index is downstairs, we shall call it to be a covariant vector. Contravariant and covariant vector. Clear? So if you have doubts here, you can ask. I think it's quite simple because we are just applying plain and simple chain rule and nothing else. So let us now see under this coordinate transformation, how does this product transform? This product, by the way, is nothing but df d lambda. If you remember, this is df d lambda. So this will transform to f prime a x prime u prime a x prime, and that is equal to f prime a x prime that transforms like del x b del x prime a f b x. And how does this transform? You have derived the transformation property, that is del x prime a del x c. I will not use b anymore because b repeated indices cannot appear more than twice. Use a different index, del x c. You see. So this is, once again I repeat, this is a contravariant vector. So anything which transforms in this way is a vector. First of all, anything and index with the index on top, I will call it to be contravariant. Index on bottom, I will call it to be covariant. Now you can see, just look at this factor and this factor. Del xb, del x prime a, del x prime a, del xc. Chain rule. If you apply chain rule, so this will be del xb, del xc. Then you will have fb x uc x. Okay. This is nothing but delta bc. fb x uc x. Now this is a Kronecker delta, right? Delta bc. So you can get rid of this Kronecker delta. So this c will get replaced by b. So you can see that this object transforms under this coordinate transformation like a scalar. It does not transform at all. So this is the transformation property of a scalar. So what is a scalar basically? If you have a function f, function of x, under coordinate transformation, it will go to f prime x prime, and that will be equal to x. This is the definition of a scalar. Anything which transforms like that, it is called a scalar. So you can see that the rate of change of the function along the with respect to the parameter lambda, by which the curve is parameterized, that particular thing is also scalar quantity. And we have learned by this, from this exercise, what we have learned, what contravariant vectors are, what covariant vectors are, what is a tangent vector, what is a dual vector, which is a gradient of a function, and what is a scalar. So we have learned all these things, all these objects and their transformation properties. Okay, good. So let us proceed further. I can at this point, we can just keep it in our notebooks, a tensor of type n, comma n. What is a tensor of type n, comma n? So let us consider a quantity T a, so there are indices here which are on top. So these are called contravariant indices, and there are indices downstairs. These are covariant indices. Okay. So this object, I will call it to be a tensor of type n, m. First of all, n and m basically denotes the number of indices on top. These are the n and these are the m. Okay, that is why n, m. So what was this UA? What kind of a tensor it is? It is a tensor of type 1, 0. And what is this one? Tensor of type 0, 1. Okay, a contravariant vector is a tensor of type 1, 0. Covariant is a tensor of type 0, 1. Now, why tensor? If this object under the coordinate transformation that I wrote down, x a to x prime a, under any arbitrary coordinate transformation, if this object transforms like this, J, and this some index if this object under this coordinate transformation transforms in this way, then only we will call this object a tensor of type n, m. Otherwise not. This is the transformation property. Please note that what I am writing, all these things are important. You have to write the arguments. If you don't write the argument, and for example, if you don't write the argument, it is wrong. If you write the argument, but if you write x, then also it is wrong. You have to write x prime. All these things are very important. So that is why I wrote x here is some x prime under coordinate transforms like this. The prime here is also important. If it has this transformation property, then it's a tensor of type n, m. But the gravitational, so we have learned about this metric tensor. What the kind of a tensor is this? The tensor of type 0, 2. Why is it a tensor? It transforms like this, in this way. It's a covariant tensor. Second rank tensor or tensor of type 0, 2. Because there are no indices on top, 2 indices downstairs. So this is a metric tensor. This is called a metric tensor.
So how can I know that this is I mean, first of all, this is a tensor, and second of all, this denotes the, I mean, this is metric tensor. I mean, we know by experience that this is a metric tensor and we can do with this. But how can we guarantee that this is a tensor? I mean, mathematically, how can we?
Oh, mathematically, okay. This is a good question actually. See, you write. Right? So how will you prove that the GAB is a tensor? These are metric coefficients, these are functions of x. How will you prove that this is a metric tensor?
Check whether it transforms.
But how? Check whether it, basically this thing transforms in this way.
So ds square will keep constant.
ds square is infinite. So if you impose that under any arbitrary coordinate transformation, x a to x prime a, the line element ds square is invariant, then you can prove that GAB transforms in a tensor. So please do it as an exercise. Keep it as an exercise. And we have already learned from the examples that we have seen in the previous class that this quantity actually describes the gravitational field that we have already seen. The metric tensor describes the gravitational field, and it is also used to define inner product between two vectors. The inner product between two vectors can also be defined by using this metric tensor. And it is also used to raise and lower indices. That is also an important thing. So by that I mean that if you have any 4 vector like this, you can write it this way. So it basically means that using this metric tensor, the contravariant metric tensor here, you are raising the index and using this covariant metric tensor, you are basically lowering the index on top downstairs. So raising and lowering. It is the metric tensor is used to lower and raise indices, and it also describes the gravitational field that we have already seen. And your question is quite pertinent. Why is this a tensor? You just demand that this is invariant under general coordinate transformations. So these transformations are called GCT, general coordinate transformations. So if you demand that under a general coordinate transformation this will remain invariant, then you will be able to prove it. It's quite straightforward. So do you want to do it on the board? Do you want to do it? Who will come? Who will come on the board? Junior? Okay. Deep? It's quite simple. Joshi, here. You want to come? Joshi, let Joshi. Because the question raised by Joshi. Next time, Manjari will know. So this is also a problem that you can solve. If this is a problem, you should show how GAB transforms under a coordinate transformation. X goes to XA goes to X prime A. X prime A. So under that transformation, ds square will go to what? ds prime square. But that is equal to what? Good, right? Please write it down. All of you, please write it down. You will only learn by writing. If you don't write, you will not learn. Because after some time you will forget everything. Whatever is being done on the board, please write it down.
But this doesn't change.
Huh? This doesn't change, so this is equal to this. Good. So ds prime square is equal to. So you write this is equal to this is equal to GAB x. What have you got? Yes, good. Yes, now you have to change it. You can change it. Good. better to use IJ, but it's better to use CD. Okay, IJ is also fine, not wrong. Okay. All these will be partial derivatives. Be careful.
Yeah, I mean, the thing is, I'm doing, just taking this side, but that is not mathematically correct.
So what will you do? What will you do?
Down the expense for third
This come. So this is a nice problem, I think. For beginners, I think this is a nice problem. For experts, it will be very simple. Good. Not alpha. See, now you should also look at the left hand side. No, you can do it. It's not wrong. I'm not saying it is wrong. It's fine. But it is good to put I and J because here you have I and J. That is what I'm saying. Okay. Good. Just follow this, you should get this. Again, partial derivative, not total derivative.
No, that will be.
Oh, that is dx, sorry. Oh, fine. Del x prime b, del xj, dxj. Now you have dxi, dxj on both sides. So you write down gix, gijx is equal to this. So by this procedure, what you are getting is a reverse transformation rather. So you have to again multiply.
That's the thing.
No, you can do it. What, whichever way you will get the same result. You could have, instead of taking this to I and J, you could have taken this to A and B.
Yeah.
Then you would get the relation directly. But since you have done it on that side, then you have to take it on that side. That you can take it. It's not a problem. Good. But you want to find G prime A function of X prime as G function of X. How will you do that? Now go to the board. Hey, go to the seat. I will tell you how to do it.
We start from the left, other than right.
No, that you can do. Then you will get the result directly. But this is also not wrong. This is also correct. But you have to take it on that side. But the thing is that you can see all you have got the result. This you just take this, just multiply del x I. You have got it. But that is not the correct way to do. That is what I am saying because you see that A and B, these indices are summed over. It is not really very good to cross multiply. No. So what you can do is the following.
Separate indices. Next time we can explain C.
And similarly the same thing on this side. Okay. So the main thing is that what we are doing here is you are putting some different indices on this side. Now at these factors here, we will get some counter factors, and from there we will get the relation, the short relation G prime X prime as Gx. So please complete that thing, and this is the reason the question that you asked was important. That how do you know that this transforms like a tensor? The reason is that the line element is an invariant under coordinate transformation. Therefore, it has to transform the metric tensor. So that is why we also give the name that it is metric tensor because it transforms like a tensor. Okay. Now we shall come to something very important. Imagine a star like this, or the surface of the sphere. Okay, and at this point you can have a tangent vector like this, right? You can have a tangent vector. Now on the surface of the sphere, at a particular point there will be a tangent plane, right? It's a tangent plane. So imagine a surface of sphere like this, and you have at this point you have a tangent plane. And on the tangent plane, that tangent plane will be attached to only one point on the surface of the sphere, and from that point there can be infinitely many vectors whose origin is that point, right? So if you have this tangent plane, so there will be many vectors, right, on that tangent plane with this on the same point. These are all tangent vectors. The important thing is that this tangent vector, you can see that it actually sticks outside the surface of the manifold. It is not totally on the surface of the sphere. Only one point is on the surface of the sphere, but overall it is outside. It is not on the surface of the sphere. Similarly, at different points, we will have different tangent planes and there will be different vectors. At this point on the surface of the sphere, this is the tangent plane. And there will be vectors like this, and this. Okay. Let me call this point P. Let me call this point Q. The question is, I want to subtract two vectors. Okay, that is not a problem. You can, so two vectors defined on two different tangent planes. So this vector is defined at Q, and this vector is defined at the point P. And I want to carry out this operation, subtraction of these two vectors defined at two different points on the manifold. The question is this a tensorial operation or not? We shall see now that this is not a tensorial operation because this does not transform like a tensor. Let us prove it. So now actually we have come to a very important concept in geometry and that we shall discuss now. So our main goal is to now what we want to do is we want to define differentiation. We want to differentiate. We want to do differential calculus on the surface of a manifold. That is our aim. And for that we have to there should be some rule by which you are able to take this vector defined at this point to this point. Our main goal, why do we subtract? Because when we subtract and then do something, some limiting procedure, we are able to calculate derivatives. Our goal is to calculate derivatives. And not only derivatives, we want to calculate derivatives which transform tensorially. I will show you now that this operation that we have here does not transform tensorially. Let us prove it. So let us consider once again, let us take this curve. This curve is gamma, parameterized by lambda. This curve is called gamma, it is parameterized by lambda, and you have points P and point Q. This I label it as, okay, here you have a vector A, C, here you have another vector A, Q. Okay, this point P I call it a XB lambda, and this point Q I call say XB XB plus DXB. Okay, so these are two that is what my goal is. I want to differentiate. So I take 2 points which are infinitesimally close to each other. Okay. So, and let us define the particular operation which I shall denote it as BAA. I shall call BAA to be this particular thing, BAA at Q minus BAA at P. And my aim is to show that this does not transform in a tensorial way. This is my aim. So let us prove this. This is A. Q is nothing but XB plus BSB. Okay. Now, since this is infinitesimally small, so we can make a Taylor series expansion. Therefore, BAA equal to AA XB plus del and higher order terms which I neglect. So I just put approximate. This order DSP square and higher orders I neglect minus this cancels. Therefore, this is equal to, I will just use a shorthand notation. Del XB I shall denote it by del B. Del B so this particular object that is defined like this is basically this. Under a coordinate transformation, once again x going to x prime, under a coordinate transformation, this will go to del prime b, a prime a, x prime. Right? So this I can write it down as del xc a prime a x prime del xc change. Okay. This thing is equal to this thing xc x prime a prime a. This is a vector, right? So it should transform like a vector. So this I can write it down as del xc. This is therefore del x prime a del x b a d x.
So when you are using the DSP term,
Let's we write it down.
No, I just look at this thing. That is a differential. That is a differential.
I mean, we know that the total thing should be tensorial or not. But
No.
we cannot say about this.
This is a differential. I am only worried about this coefficient. We'll see why in a moment. Just need to look at the coefficient part, not the differential part.
Even the coefficient parts
At second.
did not be tensorial.
Just a minute. Just a minute. No, you will be able to define it. You will get a tensor. That is what I will show you. Just a minute. Del prime b. Oh, here I have done it. Okay, I used a different index. Anyway, that is not a, okay. Just look at this part. Are you okay with this? You're okay with this, right? This differential we don't need to look at. I'm not interested about that. Because this dxd, you cannot say that this is a vector or what. It's a differential. Vector will come when you have a differentiation dxd dx d lambda, and that is uv. But this is not a vector. This is a differential. বাঁদিকটা differential, ডানদিকটা differential. Look at the coefficient. আমি তো এইটা করি। I'm not doing that. Okay. Let us come back to this thing. See, we have this part del prime b a prime a x prime equal. From here we get two terms. And what are those two terms? It will be del x prime a del x b del x prime a del x d. Then del a d x del c plus the second term is a d x del 2 x prime a del x c del x d. The two terms. And you have del x c del x prime b. And therefore, equal to the first term is del x prime a del x b del x c del x prime b del c. You know what the shorthand notation is? Del c, this means del xc. This is the first term. This multiplied by this. And the second term is this plus del xc del x prime b del 2 x prime a del xc del x d. Is it clear? So you can see from here that this term transforms like this. The first term transforms like a vector. That is how, if it transforms like a vector, see the contravariant index x prime a x d dummy, and the covariant index is the covariant index. So another dummy c b c. So this transforms like a tensor. But what spoils the tensorial property is the second term. This does not transform like a tensor, and therefore this quantity does not transform like a tensor. This does not have a tensorial property. To have a proper tensorial form, what we shall do is we shall define a different operator. we had this operator. We had this thing. We had this thing which we just now calculated. To have a proper tensorial property, we shall define a different operator, a different differential, capital D A of A, which is I define a new differential operator instead of small d, which is basically this. I define a capital D, which is defined like this. This equivalent sign means define. I define it. What is this AATP? This is, if you remember, this AATP is basically the vector defined at AAQ transported to the point P. It's a vector defined at point Q transported. So you carry the vector to the point Q. Huh? Transport. Parallel. Some transport. Parallelটা use করব আমি এখনো ইউজ করি না just little bit hang on a little bit. This part is very important. This is the main part of the geometrical part. So concentrate on this. Okay. One may write this. This is basically this. One may write this as DAA plus delta AA. Okay. What is DAA? DAA is AA at Q minus AA at P plus you have a delta AA. And what is this equal to? This is equal to this. So what should be delta AA from here?
AQ minus
This and this will cancel. So this is nothing but very good. P minus very good. Okay. কি করলাম DA is equal to eta plus eta করে ভেঙে লিখলাম আমরা this is this I put it over here and delta A, but this whole thing is nothing but this. By comparing you can get delta A to be equal to this. What I am saying is that DAA does not transform tensorially, that I have shown you just now. This transforms I want this operator or this thing DAA to transform in a tensorial way. This does not transform in a tensorial way. So this also does not transform in a tensorial way. So both of these objects do not transform in a tensorial way. The full thing transforms in a tensorial way. Okay? Good. So now, so far everything is fine. Now we have to provide a rule. So we know what dA is and what we want this to transform in a tensorial way. So now we have to provide a rule. We will say that delta AA is basically linear in both AA. It is linear in both AA and DXB. This is a rule that I am providing to you by hand. I am saying that what should be the form of delta AA? It should be linear in AA and DXB. So delta A should be linear in AB, A and DX. So linear target. But now there is a problem. You have indices to satisfy. We say you have some object gamma A. Please don't. So this is a new object. So delta AA, gamma A, BC, AB, DXC. So it is well defined. BB contracted, CC contracted. A is the free index. The free index should be on both sides, same free index. This object is called a connection. This is called a connection. So now, when I am saying that I am transporting the vector from this point to this point, there are many ways to do that transport and to define this differentiation in a tensorial way. One such way is this kind of a transport, where you are putting in an extra structure on a manifold. And what is that extra structure? This is the extra structure that you put on the manifold now, and this is called the connection. This you have to bring in by hand. There can be other ways of getting a differentiation, a well-defined differentiation thing which transforms tensorially, but there you don't need to bring any additional structure on the manifold. Here you are providing a rule by hand and bringing in an additional structure, and that structure is this connection. This gamma ABC is a non-tensorial because, as I said, that this I want it to transform in a tensorial way. This does not transform in a tensorial way, so this cannot transform in a tensorial way because the sum of two quantities, one which transforms in a tensor way, one which does not transform in a tensor way, cannot transform in a tensorial way. So if this has to transform in a tensorial way, and you know this does not transform in a tensorial way, this also must not transform in a tensorial way. Therefore, and now you have brought in this rule, you have written this delta A is linear in AB and DXC. So you have to bring in some new structure on the manifold, and then it's called gamma ABC. This is a connection. And this is some non-tensorial field. This does not transform in a tensorial way. And we will see how this actually transforms. More precisely, it's a function of x. And there are some notations that you should remember. Please don't write this as this. So see, this and this falls on the same line, vertical line. So in books you will find that they have written it in this way, but I don't know why, because nowadays you can write books in LaTeX. There is a command by which you can shift this. The problem of writing this downstairs exactly in the vertical line is that if you want to take this downstairs, you cannot come here. You have to sit on top of B. So A cannot sit on top of B. So you should give a space for him. Now if you want to bring it down, you can write it. So you should always remember this thing. We should never write it gamma A and B on the same line. This is called the connection. And with this definition, we can now write down what DAA is. So that is equal to DAA is what? Del B dxb. That is what we calculated, this term. And what is delta AA? That is gamma A B C A B C. And therefore, this is equal to, these are dummy indices. And you can say that this is C and this is B. Or you could have done it in this way. B, B, C. You can change this C, change this to C, because these are dummy indices, and therefore you can write this as del C A plus gamma A B C A B B C. Okay. So you have this quantity. Dividing throughout by lambda, we shall now divide throughout by lambda. This is kind of a curious notation. You have a capital T divided by small d lambda. Okay. So dividing throughout by lambda, this is the increment in the curve's parameter in the 2 points. This will give us basically, I will call this grad B. Okay. Okay, let me call this B for the time being. Let me call this B. This is B. This is C. B. C. Okay. So if you divide by grad lambda, d lambda throughout, and this particular object I shall call grad B, A of A, dxb d lambda, but dxb d lambda, basically grad B A, it's a tangent vector. So we have a nice relation. We have B is equal to what is grad B? This is ordinary derivative plus gamma B okay. And I will put one more property, that's gamma A symmetric. This connection is symmetric in the lower indices. This derivative is called the covariant derivative. And my demand, my claim was that this operator that we had here, this transforms in a tensorial way. So the claim is that this particular thing, or the covariant derivative here, this transforms in a tensorial way. Because this is a tensor, this is a tensor, this must be a tensor. This is my claim. So if we have this claim, then the question is from there, see, we did not specify, we only told that this gamma transforms in a non-tensorial way. And my claim is that this has to transform in a tensorial way. So from there, you can actually calculate how does this gamma transform. And you will indeed find that this gamma transforms in a non-tensorial way. We shall do it now. We shall calculate it now. So since grad B AA is a tensor, can you say a tensor of what type?
Mixed.
Mixed tensor, but what type?
One.
1, comma 1. So this is a tensor of type 1, comma 1. We are demanding that this must be a tensor of 1, comma 1. And that is how we have actually defined the differentiation of two vectors. How can you do differential calculus? How can you differentiate between two vectors? So what the physical idea was, two vectors are defined at two different points. You bring one of the vectors to this point by transporting the vector to this point, and you put in a rule that this extra part which transforms non-tensorial is linear in AB and DXC. From there, since if you define it in this way, you have to bring in an additional structure of Christoffel symbol, and from there you are going to get this relation. This is called the covariant derivative. This transforms like a tensor that you have demanded, and covariant derivative is given by this formula. So from this demand that this is a covariant derivative, therefore this transforms in a tensorial way, we now proceed to find the transformation property of this connection. Okay, let us see how does it transform. I can tell you that this is a this is you need to know the transformation property of the Christoffel of this connection. This is, by the way, this is called the Christoffel connection. We need to find out the transformation property of this object. But before even calculating, what we can say is that this does not transform like a tensor. That you can say already. So let us see how can we deduce the transformation property of this thing. So grad, let me write down this relation once again. Grad B A is del B A plus we had written it down in the following way, gamma A B. Okay, if you look at it carefully, we earlier had it as gamma A C B. So let us not put any. You are putting BC, so gamma CB you can put it as gamma BC because of symmetry. But let us keep it as CB instead of BC. So gamma is CB, and then it will be what? It will be AC. We know how this transforms. We just need to calculate how this transforms. So this, under general coordinate transformations, x to x prime, this will transform to gamma. So this is a function of x, obviously. So gamma prime A, CB, function of x prime, A prime C, function of x prime. So go to this. Is it okay? So under this will go to this, but this is equal to, this will be equal to grad prime B A prime A x prime minus del prime B A prime A. Why? Because gamma is basically grad this minus this. Therefore, gamma prime will be prime minus prime. This transforms like a tensor, so you know what it is. What should this be? This would be del x prime B. Let me see the indices that I have used. XC, I have used C. Del XC. Del X here, I think I have used D. Good. Del D. Del X prime B. Grad.
It should not be repeated.
Just a minute. Just a minute. I could make a mistake. Let me just check. A how na? A. So, A C X B X prime B, and then we have what? D CX. Because this we know this transforms like a tensor. That is what we had demanded. And this you already know the transformation property, so you just put it there. So this will be minus del x prime a. Again, I will just look at the indices del x prime a. I have used C. Okay. C del x C, and then del x b del x prime b del b. But this is only one of the terms. We have another term because this does not transform in a tensorial way, and the other term is minus. So this is there is a minus. So this will be minus del 2x prime a del x del 2x prime a del x c del c is del 2x prime a del x c del x d. There is another term multiplied by that del x d del x prime b, and there should be one a. AC, right?
That's the AD.
কোনটা
That's the AD.
AC হবে D তো কন্ট্রাক্টেড আছে
Oh, I see.
so this you just put the transformation property of this, so this will be these two terms. Good. Now what we need to do is when we have this this prime. So what you can do is you can see that you can compare, you can take these two terms. So these two terms are basically same, right? So what you can write is right? That part is common. This is this. But what is gravity this thing? This gamma a. What was that? I forgot. This is why this is quite. Let me. So it was like this. No, it was grad d. It was grad d AC minus del d AC, na? Check karo. যেটা মুছে দিলাম আমি। Grad d
DSC minus
del d AC. So that we can actually write it down as gamma c grad, হ্যাঁ এটা ঠিকই আছে, right? This is correct. This is grad d AC minus that thing. So you can see that this object first term like a tensor, it transforms like a tensor, but there is the last term which actually spoils the tensorial property. Right? So now what you have to do? কি করে গামাটাকে বার করে আনবো? What is your suggestion? How should we proceed? Huh? What is our aim? Our aim is to find the transformation property of gamma. But this gamma is multiplied by a. So what should we do now?
A prime C X prime we write it in terms of this.
Very good. So a prime c x prime you can write it down as del x prime c. Let me again see what index I have used. I've used e del x e AEX. And this is also AEX. Okay? This C is a dummy index. So you can make this E. So now you can immediately write, since AE is an arbitrary vector, just look at this line very carefully. A line ta shobar thik ache? Now see left hand side you have AE, AE, AE. Since AE is an arbitrary vector, cancel it. Good. So you have gamma prime, so the vector is gone now. Now there is nothing more to do. You can just get rid of this line. These lines are confusing. Get rid of this. Gamma prime A C B X prime del X prime C del X E. So what do you need to do now? You have to get rid of this factor.
Just multiply.
Just multiply by del X E del X prime F, both sides. So that will give us, it will be multiplied here also. So multiply both sides by this factor del X E del X prime F. So here you can see that it's gone by chain rule. Del X prime C del X prime F is what? Delta CF. So delta CF, if you contract it with this, so C will go out, this will become F. So this is also gone. So this full thing is gone. So you have gamma prime A F B prime function of X prime, that is equal to this thing. And now you can see, since there are three indices, so del X prime A del X C, contraction gamma C, then you have del X E del X prime F because of this index, contraction gamma E, and then you have this B del X D del X prime B B. So the first term transforms like a tensor. This thing is equal to this thing. First term transforms like a tensor. But then you have del X E del X prime F also multiplied by this. So that gives you the full transformation property of the historical connection, and you can see that this term follows the tensorial property of gamma. Do you have any questions? Anjali? Where are you? বলো কেটে গেছে একবার বাড়িতে গিয়ে কষে নিয়ে তাহলে কি করবে So do you have any questions at this point? Rashid, Sudeep, Pritam Goda, Devanshu. চারজন পোস্ট বেসিক আছে টানা পাঁচজন ঠিক আছে ও বলছে Is this becoming too heavy or is this okay for me? Becoming too heavy. Post basic na so heavy. Not okay. Soft. Soft. Because you know these things. You guys know all these things. Darshi? Clear? Clear? ঘুম পাচ্ছে
তাহলে সাড়ে নটা থেকে ক্লাস হবে একবার।
সাড়ে নটা থেকে ক্লাস ছিল
প্রথমে প্র্যাকটিক্যাল ছিল।
তো আমি কি ছেড়ে দেবো লেটস স্টপ হিয়ার অর ডু ইউ ওয়ান্ট টু প্রসিড
এতটুকু ঠিক আছে।
এতটা অবধি ঠিক আছে আজকে আর না আর একটা ছোট্ট জিনিস ছোট্ট Okay, let us discuss the small thing. Let us do it because we have learned what is the covariant derivative of a contravariant vector of a tensor of type 1, 0 that we have learned. Now the question, immediate question that will arise is that what is the covariant derivative of a covariant vector tensor of type 0, 1? Minus value, but let us prove it. What we have proved is that gamma does not transform like a tensor. Ektu ঠিক আছে relax করো. For just 5 minutes, let us meditate for 5 minutes. হ্যাঁ তোমরা যদি একটু ফ্রেশ হতে যাও দেখবে freshen up yourself. Go and relax. We can practically go till 10 o'clock also. But then you have to relax. It's a discussion. You should enjoy it. Don't worry about exam and anything. Just try to learn. Examination that is not very is important, but you don't need to worry about it. কি খাবার দিচ্ছে হজম করে দাঁড়া আমি এটা করে নি তারপর Shoham come. Just relax for some time. Okay, so let us now consider the derivative. If this operator, we have seen that this transforms in a covariant way. Let us consider this PAX. এটা ঠিক আছে okay now this is a derivative operator so it should obey the Leibniz rule in differential calculus so what we have is this you can write it down as dpa a plus pa
So the Leibniz rule is holding because it's a scale. Yeah, it's a scale.
PA, see, Leibniz rule is some rule in calculus that any derivative operator should in general obey that rule. Leibniz rule is such a rule. It should. Huh?
It is actually that capital T is not actually a derivative operator in that sense.
No, capital D is a derivative operator. It's not a derivative operator, it's a derivative operator. Leibniz rule is some rule that you impose. You say that all derivative operators that you have, whatever derivative, they should obey Leibniz property. That should always be there. Leibniz rule mane basically Monjari is a little bit concerned about the Leibniz rule. This is basically the chain rule of differentiation. The Leibniz rule. It's a chain rule. Chain rule আমরা সবাই শিখেছি d of u v. Chain rule du v plus v du. So this operator also has this property. It's some kind of covariant differentiation operator. What is my aim? My aim is I know what this is. My aim is to calculate what this is. Now, what is DAA? आगे देखा जाए. This is PA. This is grad B. AA. DXB. This part multiplied by d lambda. UB d lambda. Okay, that is how I define UB was DXB d lambda. So this part I know, I put it here. Plus I have DEA. Now what is the left hand side? TAAA, we have seen already at the beginning of the lecture that this transforms like a scalar. Okay? So scalar, this for a scalar, this capital D you can replace it by ordinary D. Because this also transforms like a tensor. Remember DF D lambda transforms like a tensor. So ordinary D can be replaced by capital D can be replaced by an ordinary D. Again, Leibniz rule, because all derivative operators should have chain rule, should obey chain rule. So you can write this as PA B AA plus BPA AA. This is what we have. Okay. So what should we do now? If we have this DAA, so that we will apply this we will apply a chain rule. But let's write this equation on top.
Sir, I don't understand that part. So why are we writing capital D, replacing capital D as small d?
Current capital D is small PA, but a scalar, you don't need the connection. The scalar transforms like a scalar, transforms like a tensor of type 0, 0 without the connection. You don't need the connection. Theta key energy, connection energy, capital theta. Scalar is जो capital D होता है, small d होता है. Connection the last bit. That transforms like a tensor. Because we have already shown, suppose this was FA, UA, which was F. DF, d lambda, transforms like a scalar that we have shown. So capital D taka আমি small d দিয়ে replace করে দিতে পারি. So let me write this equation on top once again. EA BAA plus BPA AA is equal to EA grad B AA DXB plus A. That's our equation. So you can remove this. Okay. Now this implies PA DAA. You can write this as DXB chain rule. I can have P দিয়ে import দেখো try করব del PA del XB DXB again chain rule. PA equal to PA এবার আমি del B A এটা বসিয়ে দেব I'll substitute what the covariant derivative is del B A plus gamma A C B Is it okay? Right? You can see that this term cancels with this term. PA this EXP. Same term. So now what do we have? Excellent. So this cancels. Did I miss any term? আরেকটা টার্ম হবে
capital DPA
দাঁড়া কোথায় মিস করেছি বলো তো
Last capital DPA প্রথম
রাইটের জায়গায় লাস্ট
ওই টার্মটা মিস করেছি না ডিপিএ এই তো বাদ এটাই মিস করেছি আমার মাথাটা গেছে ডিপিএ এ সো you have a term okay so this is the equation so let me just remove all this clutter it is not needed so what we have is B P A is equal to remove this যা আমার মাথা কাজ করছে না বুঝছো so কি ছিল একবার
just put a minus in between. I mean, before gamma, just put a minus and left side keep it same.
এই টার্মটা কি ওইদিকে ছিল বাঁদিকে ছিল
আর এইটা ডান দিকে ছিল গামা এসিবি আর ডিবিএ
so just tell me this term once again DPA
equals to মানে এখানে মাইনাস
ওইটা প্লাস হবে গামার আগে
মাঝে মাইনাস
আর গামার আগে একটা পিএ
এখানে
এখানে একটা পিএ হবে পিএ
থ্যাংক ইউ আর এইখানে একটা DXB কি আগেই ছিল তাই তো এখানে এই ব্র্যাকেটটা মুছে দিতে পারি এটা ঠিক আছে
হ্যাঁ স্যার
del PA del XB DXB AA PA fine I think this is correct right so now what we need to do is the following AA comma this DXB AC okay I am getting this kind of thing. Let me just check AA, BPA, this is equal to what? It's equal to AA, del BPA. Okay, this is fine. Gamma A, CB, AC, PA, UB. Fine, fantastic. So now what I shall do is I shall divide by d lambda. So if you divide by d lambda, throughout. But DXB d lambda is nothing but UB. And this is also UB. কিছু একটা গড়বড় আছে এখানে না?
এটাকে বাদ দিয়ে দিতে পারি আমরা
just sir in the second term we can
দাঁড়া, এক
just
second,
replace which
জাস্ট হ্যাঁ যেটাই করবো না এখানে আমার কি পেয়েছিল গামা সি গামা হ্যাঁ we have to relabel so if I relabel
Yes.
so this is C this is C This is A. That's it. Now I think the job is done, and this I can write it down as what? AUB. That is fine. So this is del B A minus gamma C AB C. A. Now this vector A is completely arbitrary. Get rid of this. This is gone. And now this I will define it as grad B CA, where grad B PA is del B PA ordinary derivative minus gamma C AB B. This part, this full thing. So you have dPA d lambda, that is grad B PA UB, where grad B PA is this. So you can see that the covariant derivative of a tensor of type 0, 1 or a covariant vector is basically given by this. So instead of a plus sign, we have a minus sign. I will just write one more result. You can find it out yourself. But there is no need to do that. You can generalize this for tensors of higher rank. So suppose if I take grad CTAB, the first term is very easy to write. It is del C ordinary derivative. So this is a mixed tensor because it's a tensor of type 1, 1. This is the ordinary derivative. The second term for the contravariant index, you have a plus gamma. Okay. You put this free index on top of this gamma A, and then you put this derivative index C here, and then just write P over here. B you keep fixed because there is only one place over here for it to go. You put a dummy index D, DT. So this is the first term, and so here you see that B remains fixed, C is already there, and for this index you put a minus gamma, here minus here, and now this will go here, gamma B. The derivative index will always go here in the gamma, so that is here. Now T, instead of B, you don't have B sitting here, so you have to put dummy index here. So, and this one will be what? B and this is A. Because A remains fixed now, B comes here, C is always there, the remaining index is D, B has to be contracted. So in this way you can generalize covariant derivatives, say T, A or gamma D, A, B, C. You can try to write this down. Or maybe this tensor of type 1, 2 covariant derivative. You can try to write this covariant derivative by following this rule. Upper index you have to put in a plus gamma, lower index you have to put in 2 minus gamma. For each lower index you have to put in minus gammas. There will be separate terms. So today what we have learned from in today's lecture is that what is a covariant derivative. So how we have a rule for transporting pressure from one point to another point. So that we have learned, and we have also learned how to take covariant derivatives of contravariant vectors, covariant vectors, and also mixed tensors of this kind. So from here we'll start the next class. So next class, I think we'll take it on Monday. Let us take it on. I was thinking of taking a class on Saturday, but let us do it on Monday. So if you have any questions, you can ask. Do you have any questions now? If there are no questions, then let us stop here for today.